Here at the Academy for Allied Health, this is Mr. Smith. We are moving through Chapter 9, going into heat. This section is a section of defining heat. Now, we've all looked at this last year when we were doing this with chemistry. So it's kind of a repeat of what we've been looking at, only now we're going to look at it more from the physics perspective of movement of molecules, movement of temperature, movement of heat, what happens physically around these changes. So we're going to go over objectives. We'll look at heat and energy. We're going to talk about thermal conduction. That becomes a new piece. We'll talk about the conservation of energy, which rears its ugly head again, and we'll try to do a problem on it. Okay, our objectives here for defining heat is we want to explain heat as energy transferred between substances and relate heat and temperature change on the macroscopic level to particle motion on the microscopic level. We've already kind of done this kind of thing. We did this last year. Yeah, we're kind of doing a repeat of it this year. Why are we looking at it again? Well, because now we want to look at it from a physical thermodynamic standpoint. Now we're not going to just be using chemical reactions to make this stuff happen. We're just going to do it physically. Okay, we're also going to apply the principle of energy conservation to calculate changes in potential, kinetic, and internal energy. It's this whole idea of internal energy and creating heat pumps that really make a big difference. That's what we're going to see. All right, so when we talk about heat and energy, heat, of course, is the energy transferred between objects because of a difference in their temperatures. Second law of thermodynamics says that this heat flows one way. It always flows from an area of high energy to an area of low energy. From the macroscopic viewpoint, that's the viewpoint where you can see it with the naked eye, energy transferred as heat tends to move from an object at higher temperature to an object at lower temperature. Okay, this is second law of thermodynamics. The direction in which the energy travels as heat can be explained at the atomic level on the next slide. And so that is, when you transfer it as heat, here's what's happening. If you take a close look, for example, you've got a can and you're shaking everything up inside. If you put a hot can, a can that you've heated up, that's got juice at 45 degrees Celsius, and you put it into the water, what happens is the juice molecules, as you can see, are moving very fastly. They're going to cause the atoms in the can to move, and that's going to, in turn, cause the movement of the water molecules. We'll see that happening. As it happens onward, if you notice on the right-hand slide, what starts to happen, notice the molecules have all started to slow down. The metallic ones look like they're moving pretty well, and even the water ones are moving a little more. You've got the water up to 11 degrees, the juices come down to 11 degrees Celsius as well. You're reaching thermal equilibrium. We actually did a lab on this. We saw how these things come down rather quickly, but that's where it is. Energy gets transferred from high energy particles to low energy particles, and the net energy transferred becomes zero. Why? Because they reach thermal equilibrium. Okay, so that's really what's going on. All right, so let's talk a little bit more. So the atoms of all objects are in continuous motion. We all know that. It's kinetic molecular theory. So that means everything has internal energy. Again, this is another reason why I say there is no such thing as cold. There isn't cold. You can't induce cold. Since we are under the agreement in kinetic molecular theory that all molecules have movement, in order to have that movement, they must have temperature. Therefore, they have internal energy. Since temperature is a measurement of that kinetic energy, and all molecules are moving, more molecules are moving all the time, then we can't say that there's anything as cold. Cold would be an induction of the stopping of movement. And really the way to stop movement is to remove high energy particles and remove the heat. So because temperature is a measure of energy, all objects have to have some temperature. Heat, on the other hand, is the energy transferred from one object to another because of the temperature difference between them. So you could say heat exists because of a temperature difference. When there's no temperature difference between the substance and the surroundings, there is no net energy transferred as heat. That should be simplistic and common sense. All right, another area with heat. Other forms of energy have symbols, of course. The symbols that identify heat, it is the letter Q. U is used for internal energy, W is used for work. We're going to be using U, W, and Q. We actually started doing that a little bit in class, but we're going to definitely be using that this week as we get through heat. Okay, because heat, like work, is energy in transit, all heat units are converted to joules, which is the standard for energy. Here's some look at thermal values. The joule, the calorie, the kilocalorie, which is the food calorie. Here's the dietary calorie, as you see, is the same. The British thermal unit. The Brits are looking at, what, 1,000 to 1,000 joules. So the BTU, the British thermal unit, is higher than a joule. It's 1,000 joules, you could say. Makes a British thermal unit. And what is that, 10 to the 8th? What the heck is that? Something like a billion, right? 10 billion, something like that, is a therm. 100,000 BTUs. Therms are used for natural gas. BTUs are used with air conditioning and heat. It is a Brit unit, British thermal unit, but it's still around and it's still looked at. So now you know how many joules that are. Usually, those of you who were involved with the Hurricane Sandy and all that, maybe your parents went out and got a portable, what's the word? A portable generator, and the generator actually comes out in BTUs. Those things you need like 5,000, 8,000, 9,000 BTUs just to try to run parts of the things in your house. Okay, so that's 1,000 joules per BTU, and you're looking at that. You know, let's say you're doing a 10,000 times that. That's a therm. You're using a lot of energy there, just to run and power simple things in your house, like run your refrigerator all the time, which is a heat pump anyway. So, all right. Let's talk about thermal conduction for a couple minutes. This is an energy transfer due to atoms transferring their vibrations to neighboring atoms. It's called thermal conduction. It needs contact. The two things must be in contact with each other. The two substances must be in contact. The rate, of course, depends on the substance. Obviously, that means specific heat. Here comes specific heat again. Two mechanisms for transferring energy are also convection and electromagnetic radiation. And we'll talk about those. We're going to talk a little bit about light and how you heat up the inside of a car when you leave things out in the sun and stuff like that. And that's convection. We'll talk about those. So a stove uses actually convection, thermal conduction, and I guess you could say the fire is electromagnetic radiation. So it uses all of those. So the handle heats up because of conduction. Convection keeps the heat all around because of the shape of the pot, of the pan. So that keeps it cooking. And then you have electromagnetic radiation. We like convection best. It describes the flow for heat for our heaters and our air conditioners, things of that nature. All right, conservation of energy. If changes in internal energy are taken into account along with changes in mechanical energy, the total energy is conserved. In other words, the sum of the changes will equal 0. So potential, kinetic, and internal will equal 0. So there you have the equation example of conservation of energy when you include internal energy. Everything is going to balance out and equal 0. Let's try a problem. right? Always going to be one. Conservation of energy. Let's see. This is a Joule's apparatus. Also looks like a calorimeter. We're going to demonstrate energy conservation. A vessel contains water. Paddles are propelled by falling masses turning on the water. This agitation warms the water. We actually showed that in class today. Or we'll be showing that in class. We're going to go over these things about how to shake this up with a flask. So make sure you got that and remember how that worked. The temperature of the water is then measured, giving an indication of the water's internal energy increase. Okay, we've actually did this. Nice simple experiment. If a total mass of 11.5 kilograms falls 1.3 meters and all the mechanical energy is converted to internal energy, how much will the internal energy of the water increase? So we're going to say that there is no loss of heat outside the surroundings. Okay, so let's see how this works, right? We've got mass of 11.5 kilograms, so it's 11.5 kilogram mass. It's 1.3 meters, it's going to go down. We have G, so we can get a potential, and we're wondering what the U is. All right, so in this case, we can say that kinetic energy is going to be 0, right? Conservation of energy, we're going to solve for the internal. Okay, we use our equation. We know it's going to equal 0. We can set up Kf minus Ke1, Pef minus Pe1. Okay, don't forget that a change in any quantity indicated by the symbol delta equals final value minus initial. So let's see how this pans out. Because masses begin at rest, the initial kinetic energy is 0. If we assume, let's say, that the final kinetic energy is going to be small compared to the loss of potential energy, we can also set the kinetic energy to 0. Okay, that simplifies things for us because it takes that out of the equation. Because all the potential energy is assumed to be converted into internal energy, that's actually what the problem is telling us. We're really just looking at the internal energy. So we're going to assume that there was no kinetic energy. Remember we said there was no transfer either in or out of the vessel, right? Didn't lose any heat. So then final potential energy should be 0. The initial potential energy should be our MGH. And so if we work this out into our equation, since our KEs are going to be 0, we really end up with MGH plus 0. Okay, we end up with MGH. So therefore the change in internal temperature is equivalent to our potential energy. Work it out, feed in our numbers, and our potential energy is 150 joules. That's the increase in internal energy. Simple problem to read and set up. Okay, don't be afraid to check those out and take a look at that. The answer can also be estimated using rounded values. So put the masses at about 10, put G at 10, then you're looking at 130, which is close to 150. And that is our looking at defining heat. We've defined it. So thanks very much. We'll get some work done in class.